I consented. All right.
We need everyone to sign this.
All right. So we are, let's see.
Run example number 9.
Example number 9. Oh, we're nailing it right now. Okay. So we're going to run through some of these examples. Did that work?
No, it's a bit too small.
Oh, let's get a bigger one.
How many plungers do you have?
More the merrier. Let's see.
I saw like 3 in there.
Special edition.
Yeah, try this one. Okay.
I think that's special edition.
Okay. Okay. What was I doing?
Oh, why does he have like real hands?
So let's check this out. After a frustrating day of canoeing. All right, so we're picking up where we kind of put off a little bit. All right, so we know force is equal to mass times acceleration. Does that work?
Yeah.
Perfect. You can just leave it there or on the desk. Thank you.
No problem.
Is this in your way? Let me move that.
Again?
Was it in your way? All right.
My way. Happened yesterday.
I know. I remembered earlier in the day. All right, so if Tonneson is lifting a box up with a constant velocity, what force is he putting on the box? Okay, so we know the box is 20 kilograms, right? What force is he putting on the box? All right, now, the only thing we got to consider here is if he's lifting straight up, what's the force acting on it? Gravity. Okay, so what we're going to do is force is equal to mass times acceleration. So mass is 20 times gravity, but he's lifting against gravity. So positive 9.8, right? So what is 20 times 9.8? 180, 190,
196.
196. Sig figs, 1 sig fig, so 200. Yes.
So it would have to be more than 200. Even a slight bit more than 200. Because if he's moving with accelerating up at the exact same force that gravity applies down, it won't.
It would be slightly, yeah.
So it has to be 200.000001.
Or since our answer was 196, it could be 200.
Okay.
Yeah.
But wouldn't, if you were to apply more force, wouldn't that make the box, wouldn't you be able to lift it high, like faster up or not?
Yeah. Yeah.
So,
You would have more acceleration. Yeah.
So you can just like plug gravity and acceleration.
In this example, since you're going straight up, yeah. Yeah.
So does the acceleration just have to be anything greater than 9.8 or like anything greater than 196 newtons, and then the answer would work? Because then you could pick up the box faster or slower than
Theoretically.
force.
Yeah.
Okay. Because that is saying like,
What's probably the minimum amount of force?
okay, right, okay.
Yeah. Okay. All great questions. All right. If Tonneson lifts the box from rest, oh. Okay, so from rest, we know our initial velocity is 0, okay, and brings it up 2 meters. So our delta x in the y direction is 2 meters. And now the box is moving. Oh my gosh, they're giving us so much information. 3 meters per second. With what force did he lift the box? Okay, so from this information, can I solve for acceleration?
Yes.
Absolutely. All right. So what I'm going to use is velocity final squared equals velocity initial squared plus 2a delta x. Right? Yes. Absolutely.
How does sig figs make the answer more accurate if they just take?
They don't.
So then why do we use them?
Science.
But like, why? It makes our answer
It's
less
like it
accurate
shows
than-
how accurate your answer can be.
Plus, how do we get 160 if we multiply 9.8 by 9.8?
By 20. Okay. So what's the acceleration here? You got 2.25 meters per second squared. Is that what everybody got for the acceleration? Okay. Now, from that, all right, what we're going to do, let's see. So if Jonathan lifts the box and brings it up 2 meters, all right, so what we have is a box, okay? And the box is being pulled up, okay? And we still have our force of gravity going down, right? All right. Now, what it's going to look like is the force applied to lift it up is going to be subtracted by the force. How did I write this? I want to make sure I got it right. Is equal to, is equal to that. All right. Where am I at? Where am I at? There we go. Force applied minus 200. If you want to use 196, that's fine. All right. And that is equal to the mass times the acceleration. Okay. If he lifts it from rest, with what force did he lift the box? Okay. This is pretty much the force of gravity, right? That's what we calculated. The force of gravity was 200. All right. So how fast did he do it? Well, you have mass times acceleration. Mass was 20. Acceleration we just calculated to be this. So 20 times 2.25 plus 200. 245? That's exactly correct. And it would be 245 because you're adding the 200 over. Okay, so the force applied is what we're calculating. We knew the force of gravity. Does that make sense? Yes.
Could you add 9.8 meters per second squared instead of doing the adding 200 newtons?
Could you have gravity here? 9.8?
No, add it to the 2.25 and then multiply it by the mass. Instead of, or maybe get a force
It's close, it's
equals mass
241,
times
so
acceleration.
technically, yes, it's pretty close, it's 241 when you just multiply
So,
or add the acceleration.
so you had 9.8.
241 is correct.
I see what you're saying.
Because
So it's
yeah,
pretty
yeah,
close,
yeah,
it's pretty close.
9.8.
Probably good.
So that, with sig figs, because it's technically 196, so, oh yeah, that's perfect then, because minus 4 from 245 is,
Exactly.
so yeah, that works, it just takes out the sig figs.
Yeah, we do that.
Yeah.
Is that going to be a very important equation that I should like star?
This equation?
No, like
F of A minus the.
Oh, force equals mass times, it's your combined forces. So it's the sum of force is equal to mass times acceleration. So you just got to add up all your forces, but gravity's pulling it down. So we were calculating how much force did it take to pull it up. Does that kind of make sense? All right, last question. If Jonathan has a maximum strength of 420 newtons, how quickly will he be able to lift it 2 meters high? Okay, once again, so we have our force applied is 420 newtons. Force of gravity, what did we say?
200.
200, okay. So there's our combined forces, right? So what's our total force? 220, okay, so 220, all right. Now, is equal to the mass, which is 20 again, times the acceleration. So what's our acceleration in this problem? $11?
Yeah.
Meters per second squared?
Wait, how do we get that?
What did you say?
Oh, you just divide.
So divide that
That's
over.
never mind.
Is it? No, it won't be 10. 10 would be 200.
So like 6 6.
We're not worried about sig figs till the end.
Oh, that's okay.
If you were to use 196, you get 11.2 meters per second for acceleration.
Very good. All right. And how long would it take him to lift it 2 meters high? Okay. How long would it take him to lift it 2 meters high? So we got a lot of information. We're going to use our velocity initial. It's 0. All right. Let's see. We know our delta x is equal to 2. Okay. What else do we know? We know acceleration was 11. We just solved that. All right. And we just got to solve for time. So what equation are we going to use?
The second one.
Okay. So delta x is equal to initial times time plus half the acceleration times squared. Okay, so let's plug it in. See what we got. I'm gonna grab a new marker here. All right, so initial velocity is 0, so I'm just gonna get rid of that part of the equation. That's pretty easy. Delta x is 2. Acceleration is 11, so half of 11 is 5.5. All right, so I'm gonna divide 5.5 and then take the square root of that. And let's see. I got 0.6. 0.6. How are we feeling on these type of problems? So, fairly good. It's force. You got to combine your forces. Combine your forces. And then just plug them in using the equations we already know. Okay? So, what I'm going to do is I'm going to go over one similar type problem, and then we'll be good to go. Let's talk about this. Where's my clicker? Oh, it's off. That will help. There we are. All right. Let's see, 10. Ooh, this is a big problem right here. Tonathan asks Billy if he can help lift one of the boxes up a hill, okay? The box is 1.3 kilograms. It's not Carl this time. Yeah.
Why does Tonathan need help moving a 1.3 kilogram box?
You never know.
You got out the hood.
All right, with Billy exerting a force F1, the magnitude of 7 newtons, and Tonathan exerting a force F2 of magnitude 11. Tonathan's force is exerted at an angle of 28 with the vertical. At what angle, with respect to the vertical, should Billy exert his force so that it will go exactly straight upwards? Okay, so I'm going to draw this out real quick. Oh, we kind of got it drawn out. All right, let's see. F1 is 7 newtons. There's 7 newtons. Let's see. F2 is 11 newtons. All right, now 28 degrees. Now, in order for it to go straight up, let me see. The x has to be equal. All right, so the x over here has to be equal to the x over there. Okay, how do we solve for x? Yeah.
So you soak the toe on 20 or for F2, and get the x, put the x on the left one, and then figure out the angle from there.
You're exactly right. Okay, so let's use sine. All right. So sine of 28 is equal to the opposite. Yeah, opposite over the hypotenuse. Okay, what's that answer right there?
5.16.
5.16. So if this is 5.16, this has to be 5.16. Okay, and now how would I solve for theta? Same thing, right? Sine?
Yeah.
All right, so in this case, I would use sine of theta is equal to the opposite over the hypotenuse. So you're going to have to do the inverse sine.
So 160.
Yep. 50? Yeah, I got 47, so 1 sig fig would be 50. 50 degrees. Okay, that wasn't too bad. To go straight up. Now, what acceleration does the box rise? Okay, so remember, we're going to have the sum of all forces is equal to mass times acceleration. Okay, there's a lot of forces acting on this, right? We got the force of Billy, you got the force of Jonathan, and you got the force of gravity is equal to mass times acceleration. Right? There's a lot of forces acting on this box right now. All right. Now, to find the force, or to find the, to find the force, what we're going to do is we're going to analyze the y direction. Okay? What is our y's? Because that's what we're lifting with, right? That's how we're going straight up. Okay? So how would I find my two y's? You could definitely use the Pythagorean theorem, or you could use, you have so many options. SOHCAHTOA, any of them. All right, so what is y in the F1? F1 was Billy. What is the y?
$8.7.
8.7. Okay, I like that. Force on the Jonathan side. Wait, is it really 8.7? It should be less. Has to be less than 7. 4.7.
Oh wait, yeah, it would be 4.7.
Okay.
I didn't know.
What's the force of Jonathan? 9.7. Okay, that makes sense. Okay. Now the force of gravity. Wait, hold on. We know the force of gravity. So we got mass. What's the mass of our object? 1.3. What's gravity? 1.8. All right. So the force of gravity is going to be whatever that number is. I need a calculator up here.
Wouldn't it be positive 9.8? Since they're moving up.
They're moving up.
Oh,
Gravity's pulling down.
Okay.
So what would that be? So negative 12.74. Okay. And then the mass of the object is 1.3. All right. Let's try to solve for it. Where did I get the negative? The force of gravity. So I have mass times the acceleration of gravity. So when you multiply those two together, you get negative 12.74. Okay. Acceleration 1.3. Sounds about right. Does that make sense? So they have to be equal, yes.
sort of still confused where you got 4.7 and 9.7 from.
The Y's, so we're lifting the box up, right? But each one's pulling at an angle. So this was 4.7, this was 9.7. So we're just analyzing what direction in the Y direction.
Okay.
So the force in the Y, force in the Y. So this was Tonathan, this was Billy, and this was gravity.
So then there was 7 the other way, but then it was this trig function?
Yes.
Okay. So how did you get the 9.7? What number?
A squared plus B squared equals C squared. 11 squared minus 5.16 squared. Take the square root of it.
You use the Pythagorean.
Where did the 11 and the 5.6?
11. So 11 came from,
Oh.
hold on.
Right there.
Right here. 11. And then, so what I used was cosine. Or no, I used sine in this one. I used sine. So sine of 28. Sine of 28 equals the opposite over 11. And 11 was given as a
So
problem.
28 degrees, the angle for both of them?
No, 28 degrees was given right here. All right, we had to solve for theta. And that's what we did in our first problem.
Okay. Wait, where did the 5.6 come from?
5.16. So you have a squared minus 4.7 squared. Actually, this 5.6, x was equal to x. So if they're lifting it straight up, one person had to pull with a certain x value, the other had to pull with the same x value to go straight up. Because if one person's x value is larger, you would pull towards you.
I understand all that. Okay.
Andrew?
For like relating to future questions, how will we know that like when they mention an angle that it's not going inverse, like inside? Would that not like lift the box? Like
So-
it's going 28 degrees to the right.
Right.
We know like based on the reading that it's not going 28 degrees to the left.
It doesn't matter.
Yeah, theoretically it won't matter.
Okay.
If you drew it out, you would draw it correct, but you get the same answer. Great questions, great questions. All right. Now, this is a very similar problem, so I'm not going to go over it, but it's the same process. Okay. What you have is you have an angle here, 45-degree angle. All right. And let's see, the crewman on a boat, one crew pulls with 130. So we have 34 degrees, 130 newtons. So if you use trig functions to solve for this, that is going to equal that, right? So from here to here is going to be the same from there to there, right? And then all you have to do is solve for your hypotenuse. Does that kind of make sense? That's all that one's asking. All right, so we're actually going to skip number 11. All right, if you want the answer, it's 102. Okay, now we're going to talk about normal forces. Okay, normal forces, the force perpendicular to a surface. All right, so we're starting to get into some inclines. All right, a force perpendicular to the surface of contact. Okay. Normal force is not equal and opposite to the weight, okay? So as you can see, if it's on a flat surface, the normal force is going up. If it's at an incline, the normal force is on the incline, okay? Gravity's always going to be straight down.
Mr. Brown,
Yes, sir.
is that because the mass of the object is pushing on the table, and so the table's pushing back the opposite direction?
Right. Yeah. Yes.
So would there be a normal force for an object falling?
For an object falling, since it's not touching a surface, no. there would be no normal force. The only force acting on that outside of air resistance would be gravity. Yes.
Okay, so what if there's an object and it's falling straight down, right?
Right.
And there's another surface directly parallel to where it's falling, and the object touches the surface. Would there be a normal force applied, even if they have no friction?
So they're both falling together?
No.
No?
The second object is static.
And you. So this is falling, and we're saying the wall is frictionless. If it's sliding on there, the normal force, yes, would indeed be that way.
But assume that they both are perfectly right next to each other, touching, but no force is being applied to it.
Well, if they're touching, there is a force applied to it.
What if the second object is also falling?
If the second object is also falling, I don't know. I don't know that one. I'll have to think about that for a second. If the second one's also falling. All right. So what we're going to learn, we're going to do some drawings. All right. We're going to do some free body diagrams, and we're just going to draw all the forces. That's all. That's the only. Did I write the definition? Yeah. All right. We're just going to be drawing all the forces. All right. That's basically what that definition is. All right. It's not too important. You're not going to be quizzed on this. We're just going to practice our drawings. All right. So this is what it is. All right. So a book at rest on a tabletop. All right. So I got a book on a table. What forces are acting on it? Gravity. Okay. So I got a force of gravity. What other force? What did we just talk about? Normal force. So normal force is perpendicular. That's going to go up. Okay. That's it. That's not too bad. Okay, number two, a regular force is applied to a book. Okay, so we got another book. A force is applied that way. Okay, so that's my applied force. Force applied to move across. What else do we know? Gravity. Ooh, I heard friction. So force of gravity, where's the force of friction pointing? Opposite direction. Okay, so the force of friction is going to the left. Force of friction. And what's our normal force here? Up. So we got force going in all the directions there. Number three, a football is moving. What happened to 4?
This is 4.
Okay.
This is 30.
Okay. A football is moving upwards towards its peak after being booted. So it's already kicked. It's already in the air. All right. What forces are acting on the football? It's already in the air.
So is it at a peak or still going up? Oh, rising upward. Okay.
Still up. Yeah.
If it's a projectile, wouldn't it be just gravity? It's just moving constant, and then the
Just gravity.
accelerating.
That's it. That's it. Yes.
There would also be drag and the force.
We're not considering air resistance yet. Yeah.
That's gonna be a whole day in school
I
when we have
cannot
to
wait.
figure out air resistance. That's not gonna be fun.
It's gonna be fun.
And A, falling from resting tree. All right, so this is the same one, just force of gravity. All right, so we're just practicing our drawing. It's basically all it is. Okay. All right. So we're going to skip 11.5 as well, because I feel like we know that. We know that information pretty well.
Why is the example 11.5?
It's similar to 11, but we're drawing it. All right. We're doing good. We're getting close to inclines, guys.
Is that why you're Russian?
Am I Russian? No, I'm European.
You're not really Russian.
Like Romanian a little bit, a little Italian. Yeah,
Okay.
some Swiss.
Okay, that one's good. good.
I am going a little fast, aren't I?
You're not going fast, it's just faster than your normal rate.
What's his normal rate?
He's accelerating.
Negative 9.8.
Acceleration.
With initial velocity of 0.
Oh,
Initial.
All right. So draw a free body diagram, break forces into components, find the sum of forces, find the sum of forces in the other direction. Okay? Makes sense, right? All right. So let us get to inclined planes. Let's do one problem. We got one more in us. I feel it. Feel it in my bones. All right.
Did you know? This is really weird to think about, but your bones are wet.
Fair enough.
They're just so weird.
Probably moist. Bones are probably moist.
I love
Not
animals.
squishy. All right. All right. So you pull a sled that has a mass of 4.6 kilograms. Okay. So our sled has a mass. Oh, let's get rid of that. Of 4.6 kilograms. Okay. With a force of 6.2 newtons. Oh, I got my force of 6.2 newtons. Okay. At a 30-degree angle from horizontal. Okay. Friction is negligible. All right. How fast is it going after 1.5 seconds? Okay. So what we're going to try to do is solve it in the x direction. Okay. How can we do that? Yeah.
Cosine of negative 30. Wait, no, it's cosine.
All right. Cosine of 30 is equal to the adjacent over the hypotenuse. All right. What is our x direction? Did they get that? 5.4? Okay. So 5.4 is our x direction. All right. Now, so we have the sum of forces is equal to mass times acceleration. All right. So we know our force is equal to 5.4 in the x direction. All right. We know the mass is 4.6. What is our acceleration in the x direction? 1.2? Is that what I heard? So acceleration is equal to 1.2 meters per second squared. How fast is it going after 1.5 seconds? So just multiply that by 1.5. What'd you get?
1.8.
1.8 meters per second is correct. How are we feeling? Starting to kind of piece it together, all these trig functions a little bit.
How was it real?
Okay. So you had your acceleration times time. So 1.2 times 1.5.
Yeah, okay. Mr. Bowers,
Yes.
is the AP exam gonna require us to like let's say like this cosine right here, we have had to go for like 3 decimals, or are they gonna just grade us and get over it?
Say that one more time.
Well, it's like, since we did 5.4, would we need to have gone maybe like 3 decimal points on the AP exam? Or like, were they?
So what you really do is you don't round this. You don't round until the final answer. Theoretically, you would just keep that long decimal in your calculator. So instead of 5.4, you have 5.3752, whatever, divided by the 4.6.
We're just using the scroll button a lot.
You got 1.8, and then 1.2 times 1.5 because it was meters
Correct.
second, and then, but you wouldn't multiply it by 1.5 again because it's second squared? Or
Well,
no?
So you got 1.2 meters per second squared. So if you multiply that by the time, which is 1.5 seconds, your seconds cancels with one of those, so you're left with meters per second. If you multiplied it by time again, you would just be with distance, and we're not worried about distance. We're worried about speed.
Okay.
How we doing? Yes.
Does the AP exam care about sig figs?
Yeah.
What doesn't care about symptoms?
Yeah. All right. And let's see, assuming that it would be a 30, with what force do you need to pull it off the ground? All right, so you just got to worry about the force of gravity mainly. Okay? Right? So what is the force of gravity in this problem? Well, we got force of gravity is equal to its mass, which is 4.6. What is gravity? Negative 9.8. Okay.
Negative 45. Yeah, negative.
Okay, so negative 45. Okay, so that's the force of gravity pulling down, right? We had negative 45.
Well, 0.08, but let's say.
Okay, so if we're pulling at a 30-degree angle, I'm going to get rid of all this data because that was the last problem. If we're pulling, well, we actually are pulling up, so let's make it positive since we're pulling up. Gravity's pulling down against you, so that's negative 45. What would the hypotenuse be? How would we solve that?
You would just divide, no, 45 would be divided by the sine of 30.
Very good. 45 divided by the sine of 30.
That gives you 90.16.
90.16, so
That's without 60.
90.
all right. Hopefully we're good on the inclined planes. Tomorrow we're going to do an experiment. We're going to test our knowledge out. All right. Good job. Good job today, guys.
Elena.
Hope you guys have a fantastic day. Tomorrow's our Friday.
Well, our Friday, not really yours.
Yeah, that's all right. Got the water bottle? Oh, man, good job.
Like stop the sound.
I'm gonna have to look that up. Two objects falling together, touching. Is there a normal force? I'll figure that out. You too.
I think I might have some kind of answer to that slightly.
What you got?
Like, well, normal force sort of depends on.
Yeah.
Well, I want to say it sort of depends on gravity. It's at like if it's on like a slope, the normal force would decrease like if the higher the slope would be, there'd be less pushing into it. So maybe there would just be such a minimal amount pushing into the force, and then there'd be like a minimal amount of force pushing into the object. There would be such a minimal amount of normal force for it to really keep those. Yeah. Sort of like this. I almost said that, but I wasn't sure.
Is it locked back there, boy? I'm so sorry. Do you want to take the shortcut? No. All right. I just thought I'd offer. Hey, tomorrow I'll have the shortcut ready. All right.
One.
How's it going?
Good. Okay. Here I am. Stop recording. Stop recording.